All right, welcome to the deep dive. Today we're taking a look at something pretty different. It's called single-flux quantum logic, SFQ for short.
Yep. SFQ.
And well, it's a completely different way of thinking about electronics, not the usual silicon stuff we see everywhere. You know, our listeners are all about getting to the heart of complex topics fast, right?
Yeah.
So think of this as your fast track to understanding this cutting edge area of computing. I mean, who knows? This stuff could change the game completely down the road.
It could. It really could.
So to really get into this, we've got two main sources. One is a presentation on SFQ logic, really meant for like circuit designers, you know, the real nitty-gritty of how these circuits actually work.
Right.
And then we've got some background on this guy, Dr. Douglas Scott Holmes. He's from DARPA.
Oh, okay.
And his expertise is in superconductor electronics and all these new computing technologies.
Right, right.
Which, I mean, that's crucial for understanding, you know, how SFQ could actually impact the real world. So today what we're going to do is try to unpack these basic principles behind SFQ logic, see, you know, could this really revolutionize computing?
Yeah.
And of course, what are the challenges, the things that are still holding it back? We'll be pulling straight from these sources, by the way, to make sure you're getting, you know, the real deal.
Okay.
All right. So first things first, superconductors. What are they? What makes them so special compared to, like, you know, regular metals?
Well, think about a normal metal, like the copper in, your wiring.
Right.
It's packed with electrons.
Yeah.
But as those electrons try to move and carry the current, they're constantly bumping into things.
Uh-huh.
Atoms in the metal, imperfections.
Yeah.
That's what we call electrical resistance.
Yeah.
And that slows them down.
It's like trying to run through a super crowded room, right?
Thankfully.
Lots of collisions. You're not getting very far, very fast.
Not at all.
So how do superconductors change that whole picture?
Well, when you cool a superconductor down below its critical temperature, and it's really cold, something amazing happens.
Uh-huh.
At the quantum level, electrons start pairing up.
They pair up.
Yeah. We call them Cooper pairs.
Cooper pairs. Okay.
And it's not like they're physically attached. It's more like they're doing this synchronized dance.
Okay. All right.
And these Cooper pairs, they condense into a ground state.
Yeah.
And there's a little energy gap. You need that to break them apart.
So it's like they're kind of stuck together in a way.
You could say that, yeah.
Okay, and I remember something about these pairs acting like bosons.
You're exactly right. Individual electrons, they're fermions.
Right.
They got to follow these specific quantum rules.
Mm-hmm.
But when they become a Cooper pair, they act like a boson.
Okay.
And the big difference is there's no limit to how many bosons can be in the same energy state. So in a superconductor, all these Cooper pairs can essentially fall into this lowest energy state and move together.
So instead of all these individual electrons just bouncing around randomly,
Right.
we've got these highly coordinated pairs all moving in sync.
Right.
So how does this super organized movement actually affect the flow of electricity?
Since they're all in sync, these Cooper pairs, they don't experience the same scattering that individual electrons do.
Makes sense.
And that has some really cool consequences. First, for a given current, they can move much faster.
Wow.
Much faster.
Okay.
And second, because they're moving so fast, their motion itself starts to affect the inductance of the material.
Really?
Yeah.
Okay.
We call that kinetic inductance.
Kinetic inductance. Okay.
So the inductance isn't just about the shape of the wire anymore.
So it's like the electrons themselves are adding to this kind of resistance to change in the current.
Yeah, exactly.
Wow. Okay. And then there's this whole thing about magnetic flux quantization in a superconducting loop.
Right, right.
That sounds pretty fundamental.
Yeah. So if you have a superconducting loop, right,
Yeah.
and expose it to a magnetic field,
Uh-huh.
the magnetic flux trapped inside, it can only exist in these tiny, discrete units.
Okay.
Think of it like money. You can have $1, $2, but not $1.50.
Got it.
So these units are multiples of what we call the magnetic flux quantum.
Oh, let's quantum.
It's a tiny unit of magnetic flux,
Uh-huh.
and it's super important for how SFQ logic works. The single-flux quantum
Right.
refers to this fundamental unit.
So it's at this level, even magnetism is getting quantized.
Yeah, exactly.
That's wild. Okay. Now, let's zoom in on the real workhorse of SFQ logic,
Okay.
the Josephson junction. What is this thing?
It's like a superconductor sandwich.
A sandwich.
You have
Yeah.
two layers of superconductor. Think of the blue areas in the presentation.
Right.
and they're separated by a super thin barrier.
Hmm.
That could be an insulator, a normal metal, other stuff. That's the gray area.
Got it.
This barrier is key.
Okay.
It's not superconducting.
So it's like we're purposely creating a weak spot in the circuit.
Yeah, exactly.
Okay.
Now, even though the barrier isn't superconducting, something amazing happens.
Uh-oh.
At this thin divide, Cooper pairs can actually tunnel or leak across it.
Tunneling.
Yeah.
Like quantum mechanics tunneling.
Exactly.
Wow.
The presentation showed how the density of Cooper pairs drops off in the barrier, but there's still a little overlap, allowing this quantum tunneling.
So they can kind of jump across?
Sort of, yeah.
Okay. And what happens then?
This tunneling has some really unique properties. If we apply a current to the junction,
Yeah.
the Cooper pairs have to squeeze through this tiny barrier,
Okay.
and to carry the same current, they got to move faster in this constricted region.
Right.
If this speed gets too high, it can actually disrupt the Cooper pairs,
Oh.
leading to a voltage appearing across the junction.
So they're like trying to push through this little tiny opening.
Right.
Okay. The presentation mentioned this analogy with a venturi. Can you explain that a little bit?
So imagine water flowing through a pipe.
Okay.
A venturi is a narrow section of that pipe.
Right.
When water flows into that narrow part, it has to speed up to maintain the same flow rate.
Okay.
It's not a perfect analogy to the quantum world,
Sure.
but it gives you an idea of how this bottleneck, the barrier in the Josephson junction,
Yeah.
forces the Cooper pairs to move faster, leading to interesting effects.
Like they're getting squeezed.
Exactly.
Okay, I can picture that.
Mm-hmm.
Now, the presentation then started talking about wave functions and phase differences.
Right.
This is where it gets a little abstract.
Yeah.
What's the, essential thing to understand here?
So every superconductor can be described by this quantum mechanical wave function.
Okay.
And it has a phase.
Right.
The key to the Josephson effect is the difference in phase between the two sides of the junction.
Okay, the difference.
Yeah. This phase difference controls how easily the Cooper pairs tunnel.
So a big phase difference means less tunneling.
Not necessarily. It's more about how this phase difference changes the relationship between current and voltage.
Oh, okay. Got it. So this phase difference, it's directly related to the electrical current.
Totally. The presentation had this key relationship.
Uh-huh.
The current through the junction is equal to its critical current multiplied by the sign of the phase difference.
Sign of the phase difference, all right.
And that critical current, it's a property of the junction itself.
Okay.
Like its area, the materials of the barrier.
Right.
The fact that it's a sine wave is super important
Why is that?
because the current oscillates as the phase difference changes,
Okay.
reaching a maximum at a phase difference of pi over 2
Right.
and going to 0 at pi and 2 pi.
So a small change in the phase can have a big effect on the current.
Yeah, exactly.
And if we push it far enough, we get this switching event
Right.
when the phase shifts by a full 2 pi.
That's it.
Okay, so you've got this current flowing, right? A certain phase difference. Then a little extra current comes along, pushes that phase difference further, and bam, when it hits 2 pi, the junction switches into a different voltage state.
Exactly.
And that voltage across the junction, that's tied to how fast this phase difference is changing.
That's right.
It's like the voltage-phase relationship.
Right.
It was something like voltage equals the flux quantum divided by 2 pi multiplied by the rate of change of the phase.
Yeah.
And there was something about a crazy high-frequency potential.
Oh, yeah. If you rearrange that equation,
Yeah.
you find that 1 volt across a Josephson junction corresponds to, get this, 483 terahertz.
483 terahertz. That's insane.
Huge. That incredibly high frequency potential is why Josephson junctions can switch so fast.
Wow.
The analogy of a damped pendulum is helpful here.
Okay, the pendulum's back.
The phase difference is like the angle of the pendulum.
Right.
The current is the torque pushing it. And the junction has some inherent damping. Just like pushing the pendulum hard enough to swing all the way around, a change in current can cause the phase to advance by 2 pi.
Leading to a switch.
Exactly.
Okay, so we've got these Josephson junctions. They can switch states ridiculously fast.
Right.
But how do we actually build circuits with them? The presentation showed a circuit symbol, talked about bare versus shunted junctions. What's the difference? Why do we need to shunt them?
So the circuit symbol for a Josephson junction is usually 2 short parallel lines connected by an X,
Okay.
symbolizing that thin barrier.
Right.
Now, a bare or undamped Josephson junction Its behavior is pretty complex. We can model it as a current source that depends on the phase difference, plus some capacitance and a variable internal resistance. The problem is they have hysteresis
Hysteresis.
in their current voltage relationship.
What does that mean?
It means if you increase the current past a certain point, a voltage appears. But when you decrease the current back down, the voltage doesn't disappear until the current is much lower,
It gets stuck.
basically.
Oh.
This makes them unreliable for switches.
Right, because you need a predictable on and off.
Exactly.
So it's like a light switch that stays dimly lit even when you turn it off.
Yeah, that's a good way to think about it.
Okay.
To fix this, engineers came up with the shunted Josephson junction.
Okay.
We add a resistor, the shunt resistor, in parallel with the junction.
Okay.
This provides critical damping.
Critical damping.
The goal is to make this parameter, beta C, be around 1.
Beta C. All right. And what does critical damping actually do?
It basically eliminates that hysteresis.
Oh, good.
When you apply a current and exceed the critical current in a critically damped junction, it switches super fast
Okay.
and generates a short voltage pulse.
Right.
But crucially, when the current is reduced, the junction quickly returns to its zero voltage state. No more getting stuck. This allows for incredibly fast switching, picoseconds, and generates millivolt range voltage pulses.
Picoseconds.
Yeah.
That's mind-blowingly fast.
It is.
And the key here is that the area under this voltage pulse, the integral of voltage over time,
Yes.
yields exactly one flux quantum,
Yes.
regardless of the specific junction parameters.
That's exactly right. It's a fundamental consequence of the Josephson effect.
Wow.
It doesn't depend on the junction's critical current or shunt resistance.
Okay, so every time it switches, it spits out one flux quantum,
You got it.
like clockwork.
Exactly.
The presentation used this analogy of a baby drinking milk
Right.
and then spitting up a flux quantum.
Yeah, it's a little strange,
Vivid.
but it gets the point across.
So can you just explain the core idea there again?
Okay, so below the critical current, the baby, the Josephson junction, is happy.
All right.
Current flows through without resistance. But if you push too much current, like overfeeding the baby, the junction spits up a voltage pulse. That's the expulsion of one flux quantum. And this spit up is basically a brief current flowing back in the opposite direction, which can then influence other junctions in the circuit.
Okay, so one flux quantum in, one flux quantum out.
You got it.
Like a little flux quantum machine.
Yeah, exactly.
All right, the flux quantum spitting baby, I'll remember that. Now, how do we actually connect these junctions to make logic circuits?
Right. Good question.
The presentation mentioned that the key electrical properties are totally different compared to CMOS, the usual kind of circuits.
Yes, totally different.
Uh-huh.
In CMOS, we use the charge on capacitors and the flow of current, controlled by transistors, to represent and manipulate information.
Right.
But in SFQ, the key players are inductance and critical current. Information isn't encoded in voltage levels or stored charge.
Okay.
It's in the presence or absence of a single flux quantum.
So the flux quantum itself is like a 1 or a 0.
Exactly. The presence of a flux quantum in a superconducting loop is a logical 1, and its absence a 0.
Okay.
The key relationship here is magnetic flux in a loop is equal to the current flowing that loop times its inductance.
Right.
And for SFQ to work, we design circuits so these quantities are on the order of a single flux quantum.
So you're playing with these values, making sure they're close to that one flux quantum.
Right.
Sometimes just below, sometimes just above.
Exactly.
Get the logic function you want.
You got it.
Okay. And what about the energy it takes to make these junctions switch? The presentation said something about switching energy being related to the critical current and the flux quantum.
That's right. The energy to switch a Josephson junction is proportional to its critical current times the flux quantum.
Okay.
And this switching energy has to be much bigger than random thermal fluctuations.
To make sure it switches reliably.
Exactly.
Okay.
And at the temperatures superconductors operate, around 4 Kelvin, super cold. We need critical currents of tens to hundreds of microamperes to make it work.
Microamperes. Okay. So if you want to use less energy per switch, you'd lower the critical current.
Yeah, in theory.
But there's a trade-off with inductance.
Right. If you reduce the critical current, you still need to maintain a flux on the order of the flux quantum.
Okay.
Since flux is current times inductance, if you lower the current, you got to increase the inductance.
Makes sense.
And this inductance comes from the design of the superconducting wires.
Okay.
We use both the magnetic inductance from the shape and the kinetic inductance from the moving Cooper pairs.
Right.
You can even use Josephson junctions themselves as inductive elements.
Wow. So it's all about finding that balance.
Totally.
Okay. Now, the presentation got into some challenges for SFQ logic. What are the big ones that researchers are still trying to figure out?
Well, one is low fan out.
Low fan out.
Yeah. Typically, when an SFQ gate switches, it outputs only one flux quantum.
Okay.
If you need to send that signal to multiple gates, you can't just split the wire. Right. The flux quantum doesn't divide like that. You need special circuits called splitters.
Splitters. Okay.
Another challenge is low gain.
Low gain.
Unlike transistors in CMOS, which amplify, SFQ gates don't always amplify much.
Hmm.
And then there's low isolation between parts of the circuit.
Oh, because of the supercurrent itself.
Yeah, exactly.
Mhm.
It can lead to unwanted interactions between nearby junctions.
So, distributing the signal, making it stronger, preventing crosstalk.
Yeah, those are all big challenges.
Okay, big design challenges. Now, to get a clearer picture, let's look at that example from the presentation, the set-reset flip-flop. Can you break down how it works?
Sure. The set-reset flip-flop is basic for memory.
Okay.
The diagram showed these blue superconducting wires and yellow critically damped Josephson junctions arranged in loops.
Right.
It all relies on this carefully controlled bias current.
The bias current. All right, so that's always flowing.
Yeah, it's a constant current just below the critical current of the junctions, keeping them in their superconducting zero-voltage state.
Like a baseline.
Exactly.
Mm.
Now, let's see what happens during the set operation. A single flux quantum arrives as input at the input loop.
Okay.
This induces a brief current pulse in that loop because of the loop's inductance.
Okay.
This induced current adds to the bias current flowing through junction
Yeah.
JDO.
Okay.
If the total current exceeds JDO's critical current, it switches, emitting its own flux quantum.
Wow.
This switching also causes a kickback.
A kickback.
Yeah, it shuts down the current in the input loop and induces current in another loop.
Okay.
This circulating current in the second loop, the storage loop, now represents the set state.
So it's storing that bit of information.
Exactly.
Okay.
This circulating current will eventually cause another junction, J1, to switch too.
Right.
This further stabilizes the stored flux quantum in a larger loop.
Making the memory more robust.
Exactly.
So this incoming flux quantum starts this whole chain reaction,
It does.
ultimately resulting in a circulating current, representing the stored bit.
That's it.
Okay. Now, how do we reset it? Make it forget.
For that, we apply another flux quantum to the reset, or clock, branch.
Okay.
This sends current through junctions J2 and J3.
Right.
These are designed so that when the reset pulse comes, J3's current exceeds its critical current first.
J3.
It switches, emits a flux quantum, and again, there's a kickback.
Or another kickback.
It shuts down current in the reset line and cancels the current in the storage loop.
So it's back to zero.
Exactly.
And the switching of J3 also creates an output pulse.
Right, indicating a reset.
Okay. Now, what if the flip-flop was already reset?
Good question.
No flux quantum stored? What happens when the clock pulse comes then?
Well, the current still flows through J2 and J3.
Okay.
But in this case, J2 reaches its critical current and switches first.
J2 this time.
J3 stays superconducting.
Okay.
J2 switching still shuts down the input current, but there's no circulating flux quantum to reset. So no output pulse is generated.
So it knows whether it was already reset or not.
Exactly. That's how it works. As memory, it remembers.
That's amazing. So elegant.
It is.
Using these tiny packets of magnetic flux and these super fast junctions.
Yeah.
The presentation mentioned different types of SFQ logic, like RSFQ. Can you give us a rundown of those?
Sure. That set-reset flip-flop could be implemented using rapid single-flux quantum, or RSFQ logic.
Okay.
RSFQ, developed back in the late 80s, early 90s, known for its speed,
Okay.
but it can have high power dissipation.
Really?
Sometimes over 90% of the power is lost in the resistors.
Wow, that's a lot.
It is.
Okay.
There's also reciprocal quantum logic, or RQL,
Okay.
uses an alternating current drive,
Interesting.
and adiabatic quantum flux parametron, or AQFP.
AQFP.
It's related to SFQ, but focuses on minimal energy use.
Okay.
The point is, there are different approaches out there.
Right. Still lots of research going on.
Exactly.
Okay. Let's shift gears a bit and talk about an expert in this field. We've got some info on Dr. Douglas Scott Holmes from DARPA. Why is he relevant to our SFQ deep dive?
Well, he's a program manager in DARPA's Microsystems Technology Office.
Okay.
And his focus is on superconductor electronics and new computing tech.
Right, like SFQ.
Exactly.
Okay.
He even worked at IRPA on the Cryogenic Computing Complexity Program, C3,
C3, okay.
all about energy-efficient superconductor computing.
So he's been working on making this stuff a reality.
Absolutely. And he's also a leader in the IE Council on Superconductivity.
Wow.
He's the Quantum Computing Engineering Chair and the Cryogenic Computing Engineering Chair.
So he's really shaping the direction of this field.
Big time.
And it's not just theory for him, right? He has real-world experience, too.
Oh yeah, tons of it. He worked at Lakeshore Cryotronics for 10 years.
Cryotronics, okay.
They specialize in cryogenic technology.
Right.
He's been involved in startups and even worked for the Air Force on superconductor stuff.
So he's seen it all.
Pretty much.
Okay. And academically, he's got advanced degrees from MIT and the University of Wisconsin-Madison.
Yep, in materials science, nuclear engineering, and engineering physics.
Wow. So he really understands the technical challenges and the real-world potential.
He does.
Okay. And his current role at DARPA means the government is serious about superconductor technologies.
Yeah, definitely.
All right. So wrapping up our SFQ deep dive, what are the key takeaways our listeners should remember?
Well, SFQ is a fundamentally different way to compute.
Okay.
It uses superconductors, operates at ultra-low temperatures, and uses quantized magnetic flux and those super-fast Josephson junctions.
Right.
It can be incredibly fast and energy efficient.
Uh-huh.
But there are still challenges with signal distribution, amplification, and isolation.
Right, those design hurdles.
Yeah.
So instead of electrons and charge, we're using these little packets of magnetic energy,
Right.
and it all happens at temperatures colder than space.
It's
And it's all about inductance and critical current, not capacitance and resistance like we usually think about.
exactly.
It's mind-blowing.
It is.
Okay, here's a final thought for our listeners. Given all this research, and experts like Dr. Holmes pushing it forward, what future applications could SFQ really transform? What breakthroughs do we still need to make it happen?
That's a great question. It could change everything from supercomputing to scientific instruments.
Absolutely. It's an exciting time for this field.
It really is.
Thanks for joining us for this deep dive into SFQ logic. We hope this gave you a good understanding of this cutting-edge area.